So the topic of today's lecture is the Sauer-Shelah lemma. It talks about a very important property of a family, which is called the VC dimension. In order to state it, I need to give a couple of definitions. So let's start with that. So we have a family, say subset of 2 to the n, and we define for any set, subset of n, a projection of a family on X is the intersections of all sets from the family with X. Then we say that X is shattered by F if we see all subsets of X in the projection of F on X. This is how we can write it compactly. Great, and finally, the VC dimension of the family is the maximum size of a shattered set, well, set shattered by F. Great, so this is an extremely important characteristics that captures the complexity of a family. It appears in statistical learning, where it originates from, the work of Vapnik and Chervonenkes, in computational geometry, model theory, and of course in combinatorics. And one of the reasons it is so important is this Sauer-Shelah Vapnik Chervonenkes lemma, which would be the main result for today. So the lemma is known under this name, typically Sauer-Shelah, but it was also proved by Vapnik and Chervonenkes several years earlier. The VC stands for Vapnik and Chervonenkes, and actually the reason for writing the two names in reverse alphabetical order is just a curiosity, I guess, because in Cyrillic, which the names originally were written, V comes before Ch. So this would be letter V and this would be Ch. So Vapnik comes before Chervonenkes, but then in the translation they didn't change the order. So this is a simple and extremely important lemma that states the following: if the VC dimension of the family is at most D, and of course the family is as usual in 2 to the n, then the cardinality of F is at most the following sum of binomial coefficients. So all binomial coefficients from zeros to the dth one. It's easy to see that the lemma is tight. You can take the following example. That's just straightforward. Replace each binomial coefficient by the corresponding family. You take all sets of size at most D, then clearly you cannot shatter any set of size D plus 1 or bigger, because, well, in order to shatter a set of size D plus 1, you need to have sets of size at least D plus 1. Great, and the proof is again via a certain combinatorial operation that we will call for this lecture squashing. Again, this result have several proofs by squashing. So first we define what squashing is. We define the following operator, Si of f. This is the ith squash. So first, Si of a set f is either f well, maybe I can actually write it just like that. F set minus I, simply. And then in case f doesn't have I, Si of f is equal to f. In case f has I, then we just remove this I. And Si of a family is simply, as before for the shifting, Si of f over all f in the family union sets f such that f and Si of f are in the family. So basically we apply squashing to each individual set as long as its image under squashing is not contained in the family. And if it is contained in the family, then we leave the set. Great. So it's easy to see that if Si of f is equal to f for all I, then f is a downset or a simplicial complex or downwards closed. There are many ways of saying this property, which is just that if f contains a set and B is a subset of A, then B belongs to the family as well. Now this is straightforward from the definition of squashing, because basically if we, can replace a set by a smaller set without making two sets coincide, then we do that. And when cannot we do it anymore is when all the subsets of all the sets are contained in the family. Great. So the next step is to show that we can always assume that the family is, squashed, so to say. That means satisfies this property. And that's the main step that remains, actually. We will show actually something more precise in the following sense. Lemma that states that basically we can apply squashes without increasing the VC dimension, but even better than that. Actually, Si of f, this family projected on X is contained in Si of f projected on X. Before we actually prove this, you should know that this immediately implies that squashes do not increase projection sizes, and thus squashes do not increase VC dimension. Thus, we can assume that, well, F is a down set for the theorem. That is, we can reduce the general case to the case of F being a down set by repeatedly applying squashes. Well, one question that arises here is why this would ever stop. Well, we can apply one squash, another squash, and maybe that would continue forever, but it's easy to see that, say, the sum of sizes of all sets in F reduces each time we apply a squash, and thus this has to have finitely many steps. Actually, it's enough to apply each squash once. Great. So now let's prove the lemma. Well, we just take y that belongs to Si of F projected on X, and then we show that y belongs to the right hand side, Si of the projection of F on X. So why is that? Well, we have two cases actually. Case 1, I belongs to y. What does it mean? It means that there exists some t in Si of F such that t intersection X is equal to y. Now, if we look at the definition of the ith squash, well, we see that if set contained I, then this is the definition of the squash on a set. So a priori we remove I from the set. But then when we apply it to the family, well, we remove it and we get this set without I, but we can also leave a set as it is in case itself and already this set squashed belongs to the family, and this is an if and only if. So this implies that t and t minus I belong to F, which implies that well, y minus I belong to the projection of F on X, just because, well, we just intersect t and t minus I with X. And this implies that, well, applying an ith squash doesn't change anything here. This implies that y and y minus I belongs also to Si of F on X. So this is case 1. Case 2 is similar, but let's do it. I doesn't belong to y. Well, let's do it a little bit quicker. So this implies that there exists t such that we have this. So this thing stays the same. Maybe let me do it this way. which means that either T or T union I belongs to F, well, because, well, something has to go into T after applying an ith squash. This implies that either Y or Y union I belongs to the projection of F on X, and this implies that Y belongs to Si of F projected on X, because, well, of course we have, if we have any of these two sets, then we must obtain Y, which is the Si of each of these two sets. So the lemma is proved, and now let's again take a look at this. So what did I say? I said that it implies that squashes do not increase projection sizes. Well, maybe I should give a little bit more details here. So this means that, well, the size of Si of F projected on X is at most the size of Si of F projected on X. Okay, let me maybe write it in a different spot. Let's write it here so that you can see what's happening. So this thing is at most Si of the projection of F on X, but we know that Si doesn't change the size, so this latter thing is just the size of F projected on X. So this is how we get that squashes do not increase projection sizes, and if they do not increase projection sizes, they clearly do not increase VC dimension. Thus, going back to the theorem again, we start with an arbitrary family F, and after repeatedly applying squashes, ith squashes for different I, we arrive at the family with VC dimension that is at most D still, and that is a downset. So going back to the proof, we take F with the VC dimension at most D, apply squashes, and get a new family, say G, such that, well, the size of G is the same as the size of F as usual. The VC dimension of G by the lemma and the arguments, simple arguments after it, is also at most D, and G being downset. Now, actually, the conclusion is immediate because, well, assume there exists some set A in G such that the cardinality of A is at least D plus 1. Well, this would immediately imply that all subsets of A are in G because G is a downset, which would immediately imply that G on A is equal to 2 to A, which would imply that VC dimension of G is at least D plus 1, which is a contradiction. Thus, and you set A from the family G has size at most D, and thus the cardinality of G, which is the same as the cardinality of F, is at most the sum that we had. So in some sense, one should think of this proof as the following argument. We basically construct an injection of any, it's an implicit injection, but some kind of injection, from a family that has VC dimension at most D to the family of all sets of size at most D. So we prove this bound by really kind of gradually getting our family with VC dimension at most D closer and closer to this example, and at last we kind of show that it's a subset of this example after all the squashes are applied. So yeah, that's it for today.